This video gives a quick introduction to the Spectral Studies Lab. In this lab, we're going to be investigating three gases, the emission spectra of three gases: hydrogen, helium, and sodium. We're going to use helium, which has several spectral lines. You'll be able to see 8 or 9 of them most likely. We'll be using that as a calibration source, and then we'll be using the calibration curve that we get from helium in order to measure the wavelengths that are emitted by hydrogen and sodium. The basic idea is that we have these three gases in tubes, as shown here. We put a large voltage across the tube, and then the gases get excited and the electrons go up to higher energy levels, and then as the electrons de-excite, they emit electromagnetic radiation, which we can then see. So what happens is as this radiation is emitted, we send it through a prism spectrometer. So here's a prism, a piece of glass. The light is bent and then goes into a microscope that we can swivel back and forth here. So you're looking at it, and there's a measuring scale across here. So what we'll end up getting is the wavelengths as a function of the angle. There's a crosshair inside of here that you'll be able to look at, and so you can put the crosshair very precisely on the locations of the lines, because the different colors will be bent by different amounts, and then you'll be able to get the wavelength as a function of the angle. So as I mentioned, we're going to be using helium first, and you'll have a whole bunch of data points like so, and wavelength in nanometers as a function of theta in degrees. You'll fit a third order polynomial to them, and you need to keep many significant figures here. I'm recommending about 10. That seems like an awful lot, but you can have large cancellations in this polynomial fit, and if you don't keep enough sig figs, your equation for this line will not fit the data very well. One thing I should mention here is that it's very easy to misidentify the lines. And if you misidentify a line, you'll see it right away, because your dots here, your data points, will not all be on a nice smooth curve. If one of them is noticeably off, then that is almost certainly because you have misidentified a line. The scale that you're going to use to measure the degree readings is called a Vernier scale. So let's take a look at how to read a Vernier scale. The basic idea is that at the bottom here, you've got degree marking, so 51 degrees, 52 degrees, etc. And on the top, you have something that goes from 0 to 29. And what you're going to do is you can get an angular reading to the nearest degree and then minute of a degree. So you're going to get the first part of the reading by looking at where the 0 is compared to the bottom degree readings here. So the 0 is past the 51 here. So that means that our angular reading is going to start with a 51. And then we're going to, because it's just past the 51 and not, the 0 is not past the half degree mark here, it's past the 51, we're going to then look and see where the top lines match up the bottom lines the best. And what we see is probably this is the best right here. And so we will add 3 minutes. So this is 51 degrees plus 3 minutes of a degree. And if we want to get that in decimal form, we'll do 51 plus, and then calculate 3 divided by 60, whatever that is, to get a decimal reading. If the Vernier scale looked like this, though, here we have that the 0 is past a half degree mark. So this one will be 51 degrees plus half of a degree, so 30 more minutes. And then if we look here, we see the 3 matches up pretty well with the line below it. So we're going to add 3 more minutes to this, and so this we could convert into a decimal reading by doing 51 plus 33 over 60. Okay, so that's how we read the vernier scale. This is obviously kind of tricky, and so I strongly suggest that you and your lab partner each make all of the measurements so that you can compare measurements and see that you get the same thing as each other. Okay, so suppose you've made your measurement now of helium, and so now you've got a third order polynomial fit of lambda as a function of angle, wavelength as a function of angle. That's your calibration curve. Now what you're going to do is swap out the helium source here and put in hydrogen, or this is the sodium source here, and you'll measure the angle where that the various lines occur at by swiveling this back and forth, the microscope, and putting the crosshair on top of various lines. You'll get an angular measurement, and then you go up from that angle and across, and that tells you what the wavelength is for those various lines. You're actually going to use your curve, though, that you get, because you have lambda as a function of theta, so you'll put in your measured theta values, and then from that determine what lambda is. Once you've measured the wavelengths for hydrogen, you can actually use those wavelengths to determine some of the energy levels of hydrogen. So it turns out that hydrogen has energy levels that the electrons can be in, and the values of those energy levels are given by this expression here. So E sub n is equal to minus 13.606 electron volts divided by n squared, where n is 1, 2, 3, etc. So as n goes to infinity, the energies go to 0, but for n equals 1, the lowest energy state, call that the ground state, is minus 13.6 electron volts. When n is equal to 2, we get minus 13.606 over 2 squared, or over 4. That's approximately minus 3.40 electron volts. And for n equals 3, we go a little bit higher, and we asymptotically approach 0 from below. So electrons can be in any of these energy levels. And what happens is that if an electron is in one of the excited states, it will quickly decay, it will lose energy and go down to one of the lower states, and to conserve energy, a photon will be emitted. So imagine that an electron starts in the n equals 3 level and goes down to the n equal to 2 level. So here's our electron changing its energy state, and then it will emit a photon, a little bundle of electromagnetic radiation, to conserve energy. The energy of the photon is actually going to be the difference in energy between these two energy levels. So to write that down mathematically, the energy of a photon, which, as we'll see soon in the course, is given by Planck's constant, a fundamental constant of nature, times the frequency, or the color, or it's related to the color of the photon. So Planck's constant times the frequency, that can also be written as h times the speed of light over the wavelength, which can also be written as 1239.8 electron volt nanometers. That's a useful conversion constant there, divided by lambda. This value here, so the energy of the photon is related to this constant divided by the wavelength of the photon, is also equal to the energy of the upper energy level minus the energy of the lower one. It turns out that the transitions that terminate at n equal to 2 here are the ones that we can see. If an electron goes from the n equals 3 level down to, say, n equal to 1, then that will be in the ultraviolet and our eyes can't perceive it. Or any transition from one of these upper levels down to n equal to 1 is not visible for us. Same thing if there's a transition from n equals 4 or above down to n equals 3, that's in the infrared and we also can't see it. But we can see transitions that terminate at n equal to 2, some of them. And so specifically what we're going to be looking at is transitions from n equals 3 to n equal to 2, and 4, 5. These are the ones that we can likely see. So let's imagine that we take as given the value of the energy level here for n equal to 2. Suppose that we know that that's minus 3.40 electron volts. What we like to do then is to determine the energies of these upper levels using this expression right here. So let's rearrange this. We'll write the energy of one of these upper levels is equal to the energy of the photon. And we can measure the energy of the photon because we're going to measure its wavelength, and then from this expression here we can get what E gamma is. So we'll take the energy of the photon and add to that E2. So we'll add E2, so that's 1239.8 eV nanometers divided by the wavelength that we measured, and then E2 is minus 3.40 eV. And then using this expression right here and our measured wavelengths, we'll be able to work out the values of these upper energy levels and compare them against the values obtained from this expression. These values for the energy levels will probably agree to approximately 1% or so. An earlier part of this video described how you're going to be collecting data for a calibration curve to get wavelength as a function of angle using a prism spectrometer, but we didn't say where the wavelengths were going to be coming from. To get the wavelengths for helium, what you're going to be doing is using our ocean optics spectrometer, which is connected to a computer. It's very nice. What you're going to do is take the spectrometer here and point it at the source, and that will give you, using the software, the Spectral Suite software, you'll be getting intensity, number of counts, as a function of wavelength. And so your data is going to end up looking like a series of spikes, different intensities, and you'll be able to zoom in on the locations of these spikes in order to find where the peak of the spike is. So this wavelength here might correspond to that value, and maybe this one corresponds to that value or something. So in part of the lab, in the ocean optics spectrometer part, you'll be getting data for intensity as a function of wavelengths, and then later on in the lab you'll be using this prism spectrometer using the wavelengths that you measured here and plotting those against angle for your calibration curve. Let me finally mention a few precautions and notes. First of all, for the ocean optics spectrometer, please don't touch the detector end of the spectrometer with your finger. That could damage it. And there's a little lid that goes over top. It screws on the end, or there might be a red plastic one that slips over the end. In any case, use that to cover up the detector when you're done. For the prism spectrometer, please don't bump the prism while you're taking data. You're making a calibration curve, which is relating wavelength to angle, and that calibration curve is going to be wrecked. If you bump the prism, you basically have to start over, and in fact there's kind of a preferred way to set things up, and so if you do bump the prism, come talk to me because I'll need to set that up again. As mentioned earlier, there's a high voltage across the spectrum tubes, and so don't put your fingers in there or something. Be very careful. When you're replacing the tubes, you should unplug the lab volt power supply or the spectrometer power supply from the lab volt one. The lab volt power supply allows you to set the voltage to various values, what you should do is set it to the lowest possible voltage that will turn the tubes on. You can go a little bit higher than that, but if you can avoid putting the voltage all the way up, that will preserve the lifetimes of the tubes a little bit. Please don't touch the tubes with your fingers. The oil on your fingers will wreck the tubes over time. And some of the sources emit in the ultraviolet, so you should wear goggles, the goggles that are provided, because they will cut out the ultraviolet radiation and protect your eyes. There's no error propagation for this lab, so it's sufficient to calculate percentage differences for the wavelengths that you measure for hydrogen and sodium, and also for the energy levels that you determine for hydrogen. So compare the values you determine to the known values. Those should mostly agree to within about 1%, but you don't need to do any error propagation.